from the De La Pietra family here, and we are again grateful for the support they provide to the center and the fact that they give us the chance to invite some of these great lecturers to enjoy in, with all they can tell us. In fact, I think this is the first time we have, for a while that we're having a lecture or a series of lectures from a pure mathematician. So we really need to try to keep some balance between physics and geometry. So Professor Fumiharu Kato is coming to give us some interesting lectures. He was educated in Kyoto. Most of I think that he got the BA, MS, and the PhD. And then he moved or was a postdoc at different positions in Europe, mostly Germany and France. And then he ended up being an assistant professor in Kyushu University, a lecturer, associate professor at Kyoto University, and full professor at Kumamoto University. Then he moved to as full professor to Tokyo Institute of Technology, from which he decided to retire and fund his own company. So nowadays he's for consulting in mathematics, and so he's the CEO of that company, and at the same time continues doing research in algebraic geometry and arithmetics. So please.
Thank you very much. So thank you very much for the introduction. And I thank Simon Center for the invitation and also for a great hospitality. So today I would like to talk about some aspect of number theory, especially its difficulty. I mean, viewed from the difficulty of some of the number theory problems. And because I'm going to talk about the difficult problems in number theory, I first start from some of the difficult problems and famous problems in number theory. So the first one, I think all of you know, almost all of you know, this is Fermat's last theorem, which has been proven by Andrew Wiles in 1994. It says, so if x to the n plus y to the n is equal to z to the n, where x, y, z are integers, where n is greater than 2, then at least one of x, y, or z should be 0. And in that case, the formula becomes to be a fairly trivial formula. So the second one is a Goldbach conjecture, which is still open. It says it predicts every even natural number greater than 2 can be written as the sum of two primes, sum of two prime numbers. And this is still an open problem. Nobody could solve it. And the third one, which I have taken here, is twin prime conjecture, so to speak. It is also a very famous conjecture, which is still open problem, a very famous open problem. It says there are infinitely many such prime numbers, p such that p plus 2 is also a prime number. So these are some famous problems, very, very hard. But I think the significance of these difficult problems in number theory lies in the fact that, these are quite simple looking. It only involves addition, multiplication, and prime numbers. And so in this sense, I think these are sort of very simple looking and so simple that even middle school student can understand the contents of these problems. But actually, it turns out that these problems are very, very hard to solve. So this here lies the significance of these problems. So in a sense, these are very, very difficult, and we do not know why it is so difficult. So I ask myself, why such a problem tend to be very difficult? Even though they are very simple looking. And here I would like to give you one answer of myself. So here is the answer. These problems involve the entanglement of addition and multiplication. That makes them extremely difficult. And I am going to convince you that this entanglement actually makes many, many number theory simple-looking problems to be very, very difficult. And so, but already in this examples of the problems, I can explain some of the some of the things about the entanglement of addition and multiplication. So here in the Fermat's last theorem, there is a mixture of addition and multiplication in the formula itself. And in Goldbach conjecture, you have sum of two primes. And prime number, the concept of prime number actually belongs to the multiplicative aspect of numbers. Maybe it is one of the most important concepts in multiplicative aspect of numbers. So it is also a mixture of addition and multiplication in this way. And the other one is also, this asks when the sum of prime plus 2 is again a prime. So, I mean, this also concerns with the primeness and also summation. Summation appears. So, in this way, it is quite easy to see that there is a certain mixture of addition and multiplication. And I am going to explain why this kind of mixture, why kind of this entanglement, I would say, makes such number theory problem so difficult. And in order to do this, let me first explain the addition aspect of number. So remember that when we first learn the numbers, maybe in elementary school or before enrolling to the elementary school, maybe you learn some of the numbers. You learn numbers by adding 1 by 1 repeatedly. So you start from 1, and adding 1 gives you 2, and adding another 1 gives you 3, and 4, 5, 6, 7, and so on and so on. And at some point, you find that you can go on this addition process infinitely many times, so that you can obtain as large number as you like. And you realize that there are infinitely many natural numbers. And you also understand that the number obtained in this way is the number in natural number system. So this is the construction by addition, and this somehow is come along with the Peano axiom, which has been posed by Giuseppe Peano in the early 20th century. But however, this method of construction, the construction only by adding 1 repeatedly, makes it difficult to understand the multiplicative structure, multiplicative aspect of numbers. Why? So the multiplicative aspect of numbers consists mainly of prime numbers, whether a given number is prime number or a non-prime number we call a composite number. And secondly, the most important aspect, multiplicative aspect, is that every number can be prime decomposed, can have a decomposition into prime factors. And this prime decomposition can be done uniquely. And this is a very significant fact about the numbers. And this really kind of is a multiplicative aspect which cannot be grasped only by addition. Okay, so here is the prime decomposition theorem. So everybody has learned, maybe in the middle school, the fundamental theorem of arithmetic. It says every positive integer has a unique prime factorization. For example, I give you this example. Just randomly chosen number, 4-digit number, 6,370. And this has a prime decomposition into 2 times 5 times 7 squared times 13. And these are the prime numbers, 2, 5, 7, and 13 are prime numbers. And I would like to display this prime decomposition into this form. So you have this display. So here, I try to use this one. So horizontally, you have every prime number ordered by size, starting from 2, 3, 5, 7, 11, 13, 17, 19, and so on and so on. And here you have a bar of length 1. I'm sorry. So here I have you can see the bar of length 1 and the height 1 because you have single 2 here. It's difficult to manipulate. I'm sorry. So anyway, so you can understand, right? There is only one 2 in the decomposition. The prime 2 appears once, and this is displayed here. That you have a single bar on the spot of the prime number 2, and you have the same height bar at 5, and you have the bar of height 2 at 7, and similarly you have a bar of height 1 at 13. So you have 4 bars in this way. So this is a very, how to say, handy and kind of a little illuminating way of displaying this decomposition. So I have this decomposition, right? And this decomposition actually characterizes the number itself. For example, if I swap the 2 bars in the middle, then you get something similar to the previous one. But this, I think, this actually is a different number. Is a prime decomposition of different number. So this tells you the unicity of the prime decomposition. I mean, this the second one is a prime decomposition of another number. Namely, it is 4,550. Right. So in this way, we can somehow display the numbers in kind of how to say? I mean, illuminative way. And every such display corresponds to a number. So this gives you the multiplicative aspect of the number in a sense. But so returning to the additive aspect of the number, and if you try to do the similar thing in just addition, then 6,370 is how to say? I mean, this is the 6,000. I mean, I'm going to say something trivial, right? So 6,370 times addition of 1, right? And 4,550 is a 4,550 times addition of 1, right? So then the display is going to be like this. So you have only one spot. It is generated by only number 1, and the length, or more properly say, the height of the bar only tells you what number they are. Yeah, and I mean they are not so. I mean the difference between them are not so illuminative. So in this way, I would say, if one only concentrates on the additive aspect of numbers, any two numbers looks quite similar, and I mean there seems no difference at all. But by contrast, concentrating on the multiplicative aspect of numbers reveals much more detailed information concerning the characteristics of each individual number. To a substantial extent, this is because there are infinitely many prime numbers, and each prime number have each face, each characteristic. So that means that the multiplicative aspect of number is more delicate and gives you much more information than additive aspect of numbers. Okay, so now comes the relationship between addition and multiplication. My slogan is that mainly the addition actually destroys the multiplicative structure of numbers, which is much more delicate information. But addition is a kind of brute force. It destroys such structure. So for watching such a phenomena, I give you one example. For example, I try to discuss this example, the addition of two different numbers. One is 2, one is a power of 2, the ith power of 2, plus jth power of 3. And what's happened in the multiplicative structure? So these numbers are, so to speak, single bar numbers. So I mean, multiplicatively, it is a very, very simple structure. And so what is the result for specific I and j? So for example, if I try to do some initial experiments, if I, for example, consider the case where I and j goes through from 1 to 5, so you have 25 cases. This vertical, I'm sorry, so I don't know how to do it, I'm sorry, so maybe I should do here. So, vertically, so this vertical is the value of I, and horizontally is the value of j. Okay, so 2 to the I plus 3 to the j is equal to, these numbers where I and j are at most 5. So, and let us go to the prime decomposition of them. Then this gives you this table, and how to read this. For example, in the uppermost, I'm sorry. So, I don't know how to. So this one, for example, consists 5, 1. So this means that the prime number 5 appears once. And the next one is 11, 1. This says the prime number 11 appears once. And so if you look at for example, the case where I is equal to 4 and j is equal to 2. So here is it. So here is this. So it is written 5, 2. That means the prime 5 appears twice. Okay. So it is actually 25. So 25 is 5 times 5. Okay. So looking at this, maybe we should extend our experiments to more cases, to look at more cases. To enlarge enlarge our table. In any case, you will find that there seems no rule. There seems no apparent rule. And all this kind of, for example, what kind of prime number appear? What kind of things? How many prime number would appear? This kind of thing cannot be predicted. It seems quite disorderly. So if I look at this, for example, the 2 squared plus 3 cubed is equal to 31, and 31 is a prime number. So it has this graphic representation. But if I go to, for example, 2 squared plus the 4th power of 3 is equal to 85. This is not a prime. It decomposes into 5 times 17. So it has 2 bars. And another one. So 2, the 5th power of 2 plus 5th power of 3 is 275. It has 2 bar number with 1 bar multiple of height 2. And you can do, such an experiment for, as many cases as you like, and you will find it seems impossible to predict how the result will really look like. So, in a sense, 2 to the I or 3 to the j, this is a result of multiplication. And if you add them, then this addition somehow destroys the nice multiplicative structure, and the result can be really chaotic. So here's another example. Even just adding 1 changes the multiplicative structure of numbers significantly. So how it will change seems very unpredictable. Here is one example. So 1,000, this has the this nice prime decomposition. So the 2 cubed times 5 cubed. And if you add 1, so then the resulting number 1001 has this cute looking prime decomposition. That's 7 times 11 times 13, but it's really, really unexpected. And the next one, this is a fantastic example actually. So you have the 32nd power of 2, and if you plus 1, then this has this kind of a very fantastical looking prime decomposition. And there is a history, backstory about this number. So it has been conjectured by Pierre de Fermat in 17th century that this number should be, this number on the right should be a prime number. But actually it was not, and this prime decomposition has been discovered by Euler in 18th century. So I like this example. But you see, plus one, only plus one seems quite complicated. Even Pierre de Fermat mistook. So now comes the one conclusion. The entanglement of addition and multiplication seems hopelessly too complicated to understand. So they are somehow entangled in a complicated way that it is very difficult to untie them, so to separate them, so to speak. Yes, so these are the sort of negative aspect of the mixture of addition and multiplication. But let us go on a little positive aspect of this thing. Namely, if you look at some of the experiments which we have done in the previous slides, we can somehow find some pattern which is maybe hidden. So if you look at this table, then it seems that each prime factor appears only once, with only few exceptions. So I count exceptions like this. There are only 3 exceptions. So there are 25 cases and 3 exceptions only. So let us enlarge the experiment. Let us extend our experiments to this. I'm sorry for the very small character. So I and j runs from 1 to 10. So you have 100 cases now. And actually, I have only 8 cases which have the multiplicity greater than 1. And all the rest, you have only multiplicity 1. That means the prime number, each prime number only appears once in the prime decomposition. So let us further extend our experiment to up to 20. So I'm sorry for this very complicated one. It's even not a table. This is just a screenshot of my laptop calculation. So let us trust the calculation of my laptop computer. So if you look carefully, then actually now there are 400 cases here, okay, and there are only 37 cases that has multiplicity 2. And if you look at furthermore multiplicity, only 5 cases have multiplicity 3, and no case has multiplicity greater than 3. So it seems that this table, the numbers appearing in this table have the prime decomposition where the prime is where each prime appears only once, except for some exception, not so many. And now comes the ABC conjecture. I'm talking about this conjecture in the second half of my talk. The ABC conjecture predicts actually these phenomena and thus reveals some of the relationship between addition and multiplication. So let me shift to the explanation of ABC conjecture, and which end up with the proof of the ABC conjecture that has been approved by Shinichi Mochizuki, and this is the last aim of my talk. So in order to explain the contents of the ABC conjecture, I have to start from a little new notation or new notions in mathematics. So which is one of which is radical. So for a positive integer d, the radical of d, written denoted by this notation, rad bracket d, is a product with multiplicity 1 of the prime factors that appear in the prime decomposition of d. So here is the examples. So 12 is decomposed into 2 squared times 3. The radical of this, radical of 12, is equal to just 2 times 3. that means that you just discard the superscript 2 in the prime decomposition. So 2 times 3 is the radical, is equal to 6. And 36 is 2 squared times 3 squared. The radical of 36, thus, is equal to 3 times 2, just same as the radical of 12. And radical of 25, 25 is 5 squared, so the radical of 25 is 5. So you just throw away the superscript. That's the principle to get the radical of the integer, starting from the prime decomposition. So this is radical. And another concept I have to explain is what we call ABC triples. A triple consisting of positive integers, A, B, and C, is called an ABC triple if the following two conditions are satisfied. The condition number 1 is A and B are co-prime. So co-prime means that, the greatest common divisor is equal to 1. And the second condition is a very simple one. It's addition. So A plus B is equal to C. So now comes the addition here. So, so here, having the ABC triple, A, B, and C, we said D is equal to the radical of A, B, C, A times B times C. So here, you have a multiplicative structure concerning about the ABC triple. A times B times C, this is multiplication, and radical. In order to get a radical, you have to look at the prime decomposition of these numbers. So D, so to speak, represents a multiplicative aspect of this triple. But on the other hand, C, which is equal to A plus B, represents an additive aspect of A, B, and C. And ABC conjecture tries to relate these two numbers. So, so in most cases, we have C is less than or equal to D, in most cases. For example, if we start from this triple 2, 3, and 5, which is an ABC triple, then C is 5 and D is 30. So 30 is much larger than 5. And 7, 9, 16, then C is equal to 16, while D is equal to 42, which is, of course, larger than 16. And 5, 16, 21, you have this. So D is larger than C. But you have a few exceptions, maybe I would say a small portion of exceptions. But there are some exceptions. For example, if I start from 1, 8, 9, then C is 9, while D is 6. So in this case, D is smaller. So you have such an exception. But if you experiment, then you will find that in most cases, D is larger than C. And this actually is the mathematical content of the ABC conjecture. Here I say, such exceptional cases seem very rare. For example, in about 15 million cases where C is at most 10,000, only 120 of them are exceptional. So a very, very small, small number of them are only exceptional. So the ABC conjecture claims actually that such exceptional cases are actually very rare. So now comes the ABC conjecture here. So ABC conjecture in one form says that for every positive number epsilon, so however small it is, we have the inequality C less than or equal D to the power 1 plus epsilon. So the power is slightly larger than 1. For all but finitely many ABC triples, A, B, and C. So this is the content of ABC conjecture. So if you have very, 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 very small positive number epsilon, however small it is, it doesn't matter. You have only finitely many exceptions. That does not hold. this inequality. This is the content of ABC conjecture. So let us go back to our experiment and try to explain our result on the experiment from ABC conjecture. So if we apply this to A is equal to the ith power of 2 and B is equal to the jth power of 3, then C is our favorite number, 2 to the I plus 3 to the j. And D is equal to the radical of ith power of 2 times jth power of 3 times C, which is equal to 6 times the radical of C, because 6 the radical of 2, the power of 2 times power of 3. Okay, so we should have, if the ABC conjecture is correct, then we should have C should be less than or equal to the 6 times radical of C itself. I have dropped off the exponent 1 plus epsilon on the right-hand side because epsilon can be arbitrarily small. Of course, this is kind of a very sloppy sort of thing to do, but still we can say, as a consequence of the ABC conjecture, the exceptional case where this inequality does not hold is very rare. So now, what we have seen in the previous experiment is that for such a number C, in the prime decomposition C, each prime seems to appear only once. That means that in many cases, C just is equal to the radical of C itself. And ABC conjecture predicts that C is smaller than or equal to 6 times the radical of C. Okay, so if a prime number P divides C at least twice, for example, then we should have this inequality written in blue. C is larger than or equal to P times the radical of C, because C appears at least twice on the left-hand side, while in the radical of C you have only once P. You have P only once, so you have to multiply P. But then maybe the right-hand side may be larger than the left-hand side. So the inequality is to the opposite direction. So this violates the above inequality if P is greater than or equal to 7. So now P can be 5, but P can be 5 or 2 or 3. But A is a power of 2 and B is a power of 3. So A plus B can never be a multiple of 2, can never be a multiple of 3. So the rest case is that P is equal to 5. And so this occurs when this this number C is divisible by 5. And of course, not only once but also has to be divided by 5 at least twice, and this is actually rare in each cases. Hence, in most cases, each prime factor of C appears only once in the prime decomposition C in many cases. So this is what ABC conjecture says. Okay, so now comes a little modern mathematical aspect of ABC conjecture. So ABC conjecture is written in the above column. ABC conjecture is known to be equivalent to several other famous conjectures, such as effective model conjecture, Spiro conjecture, and Voigt conjecture for hyperbolic curves, and many more. So it is considered to be one of the most important conjectures in number theory. So let us go on a little more technical aspect. I'm sorry. Sorry?
Who made the conjecture?
ABC conjecture. Thank you very much for, yes. ABC conjecture has been first posed by David Masser and Joseph Oesterle, so 2 persons, in about 1985. Yeah. Thank you very much. So let us go into a little more technical aspect. I do not mean that one has to read all of them. I mean, this is just a mathematical statement, which is very, very complicated somehow. But so this is quoted from Mochizuki's, Shinichi Mochizuki's paper published in 2010. So he claims, he proves that these two assertions are equivalent to each other, and has been known that the first assertion is equivalent to ABC conjecture itself. So, so he somehow reduces all this conjecture to a special case. So he says that in order to prove the first assertion, he only has to prove the second one, which is only, looking at the special case and only restricted area of primes also. And now, so I do not want you to read all of this text, but one thing I need for you to read is that here is an inequality. So here is an inequality. The inequality star. The left-hand side is a height function, so to speak. And I am now going to discuss something about height function. And I'm not going to define what height function is, but there is such a mathematical concept of height function, which is a very rich sort of mathematical concept. And in a sense, ABC conjecture reduced to upper bound of height function, like this inequality. So now I go to another avatar of height function. So in order to solve the ABC conjecture, so I'm now going to explain the solution by Mochizuki of ABC conjecture. So in order to do that, he has to interpret the height function in a different way. So the height function is essentially equal to the sum of the degrees of the so-called Q parameters at bud primes. So I'm sorry, I do not explain what bud means. But if a prime is bad, then a certain mathematical object, which is called elliptic curve, has bud reduction. It has a kind of a special sort of structure on it. And from this, you can read off some special parameter, which is called Q parameter. And so what am I saying is that in order to show the ABC conjecture, you have to show the upper bound of height function. You have to show then the upper bound of this Q parameter. So this is the reduction step. So how to obtain the bound? Here is the outline. So multiply. So we are now going to upper bound the degree of Q, the parameter Q. So we would like to show that the degree of Q is small. And in order to do that, so the sort of the typical way of doing is the following. So you multiply degree of Q by a number, maybe large number, and try to show that the result is not so different from the original degree. So the difference is only by adding some small number c. So L times degree Q, which is of course larger than degree Q. But if degree Q is very small, then L times degree Q may not be so different from degree of Q. It is only different, and the difference only differs by adding by some small number. Then we have a degree Q is upper bound by this number on the right-hand side, which means that the degree Q is small as desired. And in principle, this gives you the inequality like ABC conjecture. Okay, how can it be done? So here, from here, I would like to explain the content of the so-called inter-universal Teichmüller theory, which has been developed by Shinichi Mochizuki, and has been accepted by mathematical journal publication REMS 2 years ago, and has been already published. Okay, so in this theory, which solves the ABC conjecture, he introduced a new notion which is called Hodge theater. So here, the Hodge theater is, in a nutshell, a set of mathematics. So this somehow conveys you a kind of mystical sort of object. But actually, this is not. I mean, the Hodge theater actually can be described entirely in terms of ordinary and conventional mathematical notions and objects like category, groups, monoids, and so on and so on. So this is, however, mystic it sounds like. I mean, the object itself can be defined in a conventional mathematics. A little more precisely, it is a system of mathematical objects that are necessary to carry out the procedure described above involving elliptic curves, schemes, algebraic number fields, and so on, whatever that means, translated into the language of groups, such as fundamental groups, Galois groups, and monoids using the method of an abelian geometry. I'm not going to explain this in a more, more plain words. So, I mean, this is very, very technical. I'm very sorry, but I'm going to explain this in a more, non-professional way. Okay, so here is the first outline of the proof. There is a, so here you have, you prepare two copies of Hodge theater. These are conventional mathematics. And then you pose the so-called theta link between them. Here, the theta on the left-hand side. This somehow represents the power of Q. So so we take the set of powers of Q rather than a single power of Q for some technical reason. And on right-hand side, you have single Q, the parameter Q. And you link these two, so to speak, the theater of mathematics in such a way that this Q to the power something is linked or related or equal to the single Q. So this is, so to speak, the gluing of two objects, in two mathematical objects, which is, of course, not compatible with all the mathematical operations like addition, for example. So by this link, you can share multiplication, but addition cannot be shared. But this sort of gluing is kind of a usual way of doing in the conventional mathematics. For example, you would like to construct a space out of some basic space by gluing. And what you do here is very, very similar to gluing. So you have some mathematical object on one hand, and the other hand you have the same copy of the mathematical object, and you would like to glue in a non-trivial way. So this is what we do here. So not so exotical sort of things. Yeah, and now we do some algorithm which we call multi-radial algorithm, which I'm going to explain in the end of this talk. And from this, you will deduce that actually the degree Q is nearly equal to the degree of the power of Q. And that gives you the answer for that gives you the desired result, as I have explained before in the previous slides. So in order to explain what is going on in this picture more closely, so let me start from the more principal sort of argument, starting, for example, explaining what is the an abelian geometry aspect in this picture. Okay, so in order to do this, let me start from what symmetry is. So it's a very, very simple sort of thing. So symmetry. So what is symmetry? So here I put a square here. A square is symmetric with respect to the 90-degree rotation. That is, its shape does not change when rotated 90 degrees. So this is obvious, right? So this means that square has symmetry, certain symmetry by rotation of 90 degrees. So this is what symmetry is. Okay, in mathematics, an object X, whatever it is symmetric with respect to an operation F. if when applied to X, the operation F preserves the structure of X. The set of operations that preserve the structure of X form a group. That is, if F and G are the operations in this set, then one can compose them. GF, which is to say apply F and then G. Then this also belongs to the set. The second one is there is an identity operation. That means you do nothing. So this we usually call identity operation. And thirdly, each operation in the set F admits an inverse operation. So the 90-degree operation clockwise has the inverse operation which rotates to the other way around. Okay, so this is symmetry and groups. So now comes a little observation. So we usually start from object and then discuss symmetry. And we would like to make it opposite way. Namely, we start from symmetry, then asking whether we can reconstruct the object from symmetry or not. So this is actually the most important question in an abelian geometry, which is one of the most technical tool used in IUT, interuniversal Teichmüller theory. So namely, I'm asking, is it possible to recover the object from its group of symmetries without using any other data? So only by symmetry can you recover the mathematical object itself. So if it is possible, then we can use symmetry to teleport object. I mean, this is a story in mathematics, okay? So you have a two world, left-hand world of mathematics and right-hand world of mathematics. Okay, so you start from an object, and you take, you read off the possible symmetries of that object, and you transport this symmetry to another universe of mathematics, and you try to reconstruct object from that symmetry. Okay. So this is like this. So this is like making a communication by maybe mobile phone to another planet. I mean, talking only about the symmetry, can you really send the object to this another planet or not? And here comes the situation of the theta link. So in a situation like the one involving the theta link, which is not compatible with the mathematical operation like addition, where not so much information can be shared between these two theaters, the object itself cannot be exchanged, but communication by symmetry is still possible to some extent. And here the important point is that there are two operations in the world of numbers, addition and multiplication, and we are wondering about the entanglement of these two operations. But there is only one operation in a group of symmetries. So the communication by group or symmetry is much more easy, much easier. Okay, of course, but of course, I mean, symmetry alone does not always allow one to reconstruct object perfectly accurately. In other words, communication by symmetry is typically accomplished by some sort of distortion or indeterminacies. So this kind of inaccuracy is inevitable. But in principle, the more complex the symmetry group is, the more accurate the reconstruction of object from the symmetry will be. For example, the square may not be accurately reconstructed from the symmetry, but maybe the hexagon has a little more chance to be reconstructed from the symmetry because the symmetry group is a little more complicated. And thinking about n-gons, where n is large enough, then maybe you can a little more accurately reconstruct the original shape. So now comes the abelian geometry. So an abelian geometry is a theory in mathematics that aims to reconstruct arithmetic or algebra geometric objects from their associated symmetry groups, such as fundamental groups and Galois groups. The term an abelian means in the sense that these groups are sufficiently complex. So, I mean, it comes from the term abelian. So, abelian group is a kind of thought as a most simple group, and an abelian is somehow far from abelian. So it's very, very complicated. I mean, so much complicated from being abelian group. So if it is complicated enough, then you have a good chance to reconstruct the object you like. So historically, an abelian geometry began with a certain conjecture by Grothendieck. This conjecture was ultimately completely solved by Shinichi Mochizuki of Kyoto University, so we are not talking about him. To this day, a group of researchers, including Mochizuki at the Research Institute for Mathematical Sciences of Kyoto University in Japan, continues to conduct pioneering research in abelian geometry. But of course, I mean, there are many, many experts in abelian geometry all over the world. This discipline has been studied, I mean, tens of years ago, like 50 years ago. I mean, starting from the conjecture by Grothendieck. So this now I have explained the, so to speak, the principle of the abelian geometry. So Mochizuki's mono-abelian transport, so to speak, realizes the teleportation of objects, so to speak, mathematical object, that we discussed about. So you start from object on the other hand, and try to reconstruct the object on the on the right hand side by communication by symmetry. Okay, so now I have 5 minutes left or 7 minutes left. So in this 7 minutes left, 7 minutes, I would like to explain the final part, which is about the multi-radial algorithm, which is the algorithm to compute the degree of Q. So this is the final part, actually. So we, so remember that we have prepared 2 copies of theaters, and to distinguish, we label dagger here and double dagger on the right-hand side. Okay, and we set up a kind of a data, which is called, so one is called radial data, and also the copy of the radial data on the right-hand side. And they are related to the, what is called core or choric data. So the radial data, so to speak, is a data for computing the degree of Q. So this is a necessary, it's a set of necessary data to run the algorithm to compute the degree of Q. So you have the same copy here. And the core is a set of set of data, I mean, in terms of groups and monoids, set of data which can be shared between these 2 theaters. So quite reasonably, the core data is quite restricted because, I mean, these 2 theaters, the relationship is restricted. They cannot share, for example, addition. Yep. So in this way, IUT theory wants to separate addition and multiplication. Okay, so sorry, maybe. So from the radial data, you have a projection to the choric data. So although much of the structure of radial data is lost, when one passes to the choric data downstairs, the relationships, morphisms between the different collections of radial data, different objects, the relationships are projected surjectively to the relationships downstairs. And that is to say, I'm sorry. I don't know what's going to happen. So therefore, certain algorithm that can take radial data as input can be expressed in terms of choric data without using any other data. So already some of the object can be transferred to the other theater by using this communication with symmetry. And moreover, the relation between two objects here on the radial data can be projected to surjectively onto a certain relation. So this relation can lift it to the other way. That means that the relation can also be somehow transformed to the other theater. So in that way, somehow we can synchronize the algorithm to go parallelly. Even though, I mean, these two theaters are related in a very, very restricted way. So now we execute a multi-radio algorithm, so to speak, for which the only required input data is choric data compatible with the theta link, where we recall that the theta link destroys the additive structure, which is so-called the holomorphic structure in his paper of the numbers on opposite sides of the theta link. So we now execute the multi-radio algorithm and to get the result. And what are the results? Because we synchronize the algorithm to compute the degree. So on the left-hand side, you come up with the degree of the theta, which is the set of some powers of q. And similarly, you have also a degree of double dagger theta, which is also a set of the same copy, the set of powers of q. And because they are synchronized, you can show that these two degrees on both sides can be nearly equal. And remember that we, okay, so now comes the explanation. Multi-radio algorithm appears a priori to require radial data as input, but since the algorithm can in fact be expressed solely in terms of choric data, the output data that appears on the opposite sides of the theta link may be regarded as equal up to relatively mild indeterminacies. I mean, I'm not saying they are precisely equal, but they are nearly equal up to some indeterminacies or inaccuracy, okay, which is inevitable. Okay, so remember that we have a theta link between them. And this theta link somehow destroys the holomorphic structure, so to speak, the arithmetic structure on both sides. So you have theta, which is the set of the power of q, is linked to a single q. And this is not compatible with the addition of both sides. But nevertheless, you have something we share between these two theaters. And only using that data, basically, we can come up with the computation of the degrees of theta, which is nearly equal. Now, so this is actually the end of the proof. So degree dagger theta is nearly equal to degree double dagger theta. Dagger theta is like q to the n. In the left-hand Hodge theta, and double dagger theta is like q to the n, also like q to the n in the right-hand Hodge theater. So if you like, so in the right-hand Hodge theater and left-hand Hodge theater. Okay. So, and two Hodge theaters are related by this link. Q to the n is linked to the single q, the theta link on the bottom. Hence, degree q to the n and degree q are nearly equal in the right-hand side. Okay. So this is, I mean, so linking and that nearly equal should be read at the same time. So this and that implies that the degree q to the n and degree q are nearly equal. And that is the desired nearly equality. This shows that degree q is small, which in principle gives the desired upper bound of the height function. So now my time is running out. So just I would like to give you a short summary what I have talked about. Problems in number theory can be extremely difficult because they involve entanglement of addition and multiplication. The entanglement of addition and multiplication seems hopelessly too complicated to understand. That was the conclusion of my first half of my talk. ABC conjecture predicts some relationship between addition and multiplication, as we have seen. IoT theory, inter-universal Teichmüller theory by Shinichi Mochizuki, solves ABC conjecture by considering different copies of mathematical theaters, which are, however, defined by means of conventional mathematics, and thus separating addition and multiplication. So this was the sort of the strategy for having the ABC conjecture by his theory. So as a final remark, I'm sorry. So final remark, I would like to remark the following things. So there are actually several expository papers by Mochizuki himself that explains the ideas of IoT theory. So I have now explained some of the ideas in IoT theory, but some others maybe you can find in his expository papers if you like to read. And all of them can be freely downloaded from his homepage. So please look them up. And especially my recommendation is, so my favorite one, is on the essential logical structure. So this is a title. It has a very, very long title on the essential logical structure of inter-universal Teichmüller theory in terms of logical and logical or relations. Report on the occasion of the publication of the 4 main papers on the inter-universal Teichmüller theory. So this paper has been updated. I think the last updated this month. And it's like 150 pages long, so it is very long. But it is, I mean, compared to his 4 papers, it is more than 800 or so. So it's much shorter. So I think it's a lot of fun for you to read this one. So my recommendation. Okay, so thank you very much.
Are there any questions? Yes.
Okay, so you said about the symmetry of addition and multiplication. What are those? And how are they related? So you mentioned this transfer of information of the symmetry group of addition and multiplication. So how precise can you say about the symmetry of these 2 objects, and how precise are they related?
Well, the symmetry which is communicated between the theater is in terms of the Galois group of fundamental groups, which is, interpreted in a sort of modern mathematical objects. And so in a sense, the 2 operations in number, this gives you many mathematical objects like spaces in algebraic geometry. So if you have both addition and multiplication, that means that you also have this kind of algebraic geometrical spaces, schemes, and many object in number theory. But if you stick to this situation where these 2 operations are, there in one place, and try to develop all the rest of their theory, then you cannot separate them. And that was the point. In order to separate addition and multiplication, you consider 2 copies of the, so to speak, math theater, and try to restrict the relationship which can be shared between these theater, and try to communicate in a very restricted situation, and try to do the algorithm for computing the degree of Q. So do I answer your question? I'm sorry.
I want to get some precise information. Suppose I know all about geometry. How precise can you get?
You mean the precise relationship between addition and multiplication?
The group that you can write down, particular group that.
Yeah, the group. Yes, the group can be written. Particularly. Just definitely. Yes.
Abstractly defined or sort of.
Well, in mathematics, there is kind of a. The distinction between abstract and concrete is quite vague sometimes. Of course, they are very abstract, but in a way, they are very concrete. These are the fundamental group on such and such spaces, the Galois group of such and such number fields, and so on, like this. So this can be, I mean, very, very explicitly written in this sense. Okay.
Well, thanks for the nice talk. I
you very
have two questions. The first is there an upper bound for the number of pairs that may violate the conjecture?
I'm sorry? Excuse me.
There is an upper bound on the number of pairs that violate the conjecture?
You may, so your question is about the upper bound we finally obtain, which is related to the inequality that appears in the ABC conjecture. Is that your question?
Exceptions.
Yes.
The exceptions. Oh, I see.
The number of exceptions.
Oh, I see. Yeah, I mean, in order to estimate, in order to have the explicit estimate of the number of exceptions, you have to really evaluate the upper bound, right? And this has been done to some extent by a quite recent paper by Mochizuki and some other people, which has already been published from a journal.
So it is known. Well, it is known the number of upper bound.
Yeah, some upper bound is quite explicitly evaluated. Yes.
I see. Okay. So the other question is: you are using the concept of entanglement, referring to the relation between this addition and multiplication. Entanglement is what is the basis for quantum information. Okay, it's the basic concept in quantum information. But it's just using a nice name, or there is more to it?
This was not my intention. I'm sorry. So I used the word entanglement, but I do not have any, I mean, quantum mechanics connotation to this. Just very, very mixed in a very, very complicated way.
Well, there's also teleportation in quantum information.
Maybe.
Any more questions or comments? Yes, Kenji.
You can speak Japanese if you like.
No, in the document you recommended to read, there's a logic and logic or appeared. Is that the same thing as multiplication and additions?
Oh, it is not precisely like that. I mean, addition and multiplication is not precisely corresponding to and or. And or is like, so let us go back to slides a little. So, okay, so here in the explanation, I said that this link and that equality gives you the desired upper bound, right? And here I said and this and should not be or. And that's the main content of and or distinction, okay?
Any more questions or comments? Out of curiosity, how many people understand the proof?
Well, well, I think, well, I don't know. So for me, people think that I...
Upper bound.
Well, finitely many, right? I don't know. So I would say maybe not 100 nowadays still. So I myself do not understand in the extremely detail because I'm not an expert of abelian geometry. So I have to somehow leave black boxes, some very, very technical abelian geometry sort of thing. But abelian geometry is a very, very old discipline, and everything is already established. So I think I can just rely on the known result to read the outline of the proof like this. Yeah.
Thank you. Any more questions or comments? Yes.
What's the core of addition and multiplication?
What is that?
What's the core of multiplication and addition?
Yeah, that's a little bit difficult to figure out. So things are not so simple, like core is multiplication and radial data is addition. I mean, these data also contains both addition and multiplication to some extent. So roughly speaking, the radial data involves some group theoretic structure that comes from geometry, that comes from algebraic geometry, arithmetic geometry. So it consists of a geometrical sort of information, and core is mainly on the Galois theory. It consists of the symmetry of number fields, which lies in the base of the space. So things are not so simple. Like core is something like addition or multiplication. So yes, right. Galois group and fundamental groups.
There are two Galois groups which are isomorphic.
Yeah, this kind of thing. Yes, I mean these consist of the. More precisely speaking, the Galois group has already been somehow interpreted into a categorical language, not the group themselves, but molding out by this categorical sort of thing. I mean, this core consists of some Galois group sort of information, and together with some relationship between them, and similarly to the radio data. Did I answer your question?
Well, I don't see any more questions or comments, so let's thank our speaker again.
Thank you very much.
What was the
Thank you very much. A lot of was over my head. That's not there's some sort of, you know how you represent things in terms of primes, the histogram sort of, okay, that had occurred to me. Now, what's interesting is one way to do that is to start with the largest thing and you work down, you start with the largest prime, you work down to 2, and you write down these numbers, okay? For instance, you have 2, 3, 5, okay? 25 would be represented by 2, 0, 0.
Yeah.
Right?
Yeah.
Okay, in base 10, it's represented by 25. It's different. Okay, question, are those two numbers ever identical? Turns out I found one case where they are.
No. I mean,
There is one case where it is, and my conjecture is that it's the only case. The number 12. The number 12 is 12.
Okay.
It's 2 times 3 times 3. It's 2 times 2 times 3, right?
2 times 2 times 5?
Okay. No. 2 times 2
Oh, I'm
times
sorry,
3
you
is
got
12.
12.
Okay, 3 times 2 times 2.
Okay.
So when you write it down, it has 12, it's 1, 2, and base 10. When you write it down to your system, it's 3 times 2 to the second, which is 1, 2, and they're equal.
Oh,
The conjecture is that's the only number for which true is. I have no idea whether it's true.
Okay. Thank you very much.
Anyway,
That's interesting.
you obviously you have some sort of homepage. It has like a mailing address, obviously. If I want to send you something, I can send it to you.
Yes. Yes, please ask the people here in the service. So they know how many to reach.
Okay, yeah.
This way, so.
Okay, yeah, sure. Thank you very much. I
Thank
really
you.
appreciate it. I hope you get here for the next few days, I'm not sure.
Thank you very much. Should I take it? Or should I do something? Microphone is on. Thank you.
may drop. I think I might have, I thought I might have dropped something. Very irritating. I dropped it. I dropped it in the wrong pocket. Okay. All right. Thank you for taking care of these. It's interesting. I'll be slightly incomprehensible.